In the previous lecture, we talked about ISAM, which is a static indexing structure based on the graph theory, which is basically a tree. There we observed that the non-leaf nodes are fixed once they are created, whereas data is stored in the leaf nodes, and the long overflow chains may form if the data is increasing. Now we observed that's a drawback of ISAM. To alleviate the problem of long workflow chains or the performance of the ISAM, a new kind of indexing structure is proposed, again based on trees, but this time the possibility of shrinking or growing of the tree is taken care. So as the data grows, there should be a provision to expand the tree, and as the data decreases, the provision should be there to shrink the tree. So that facility is added in, and a new kind of indexing structure is proposed in the name of B+TREES. A B+tree is a special kind of a tree with certain restrictions. Basically, it's a height balanced tree, and it is decided with a parameter D, which indicates the capacity of the tree. Every node contains m entries, where m lies between two bounds of d and 2d. Suppose if I take the capacity d as parameter as 2, then every node should contain entries. A minimum of 2 entries should be there, and a maximum of 4 entries can be there. This dictates the capacity of the tree, because it dictates the capacity of the node entries, where m indicates the node entries. And every node contains the key values and the pointers. Just like in the ISAM, it has key values and pointers. If there are m index entries, then m+1 pointers will be there, pointing to the children of the node. And in B+TREES, 50% of occupancy is guaranteed. If at all it falls short of that, some kind of readjustment of nodes has to be done. And if it is full, then again, if you want to insert something, then a readjustment of the nodes has to be done. So 50% of the node should always be filled at any point of time. There is another restriction that is kept here. So just like in ISAM, every node will have keys and pointers to the children of that. And the leaf node contains the data records or pointers to the data records. Another important feature of this B+TREES is that the leaf nodes are doubly linked, forms a doubly linked list. Unlike in the ISAM, the leaf nodes forms a doubly linked list. This actually facilitates range queries, whereas in ISAM that's not the case, and it doesn't support range queries. Whereas B+TREES supports range queries because of the add-on feature here that the leaf nodes are doubly linked lists, in the form of doubly linked lists. And these are the important features of B+TREES, and we'll see how actually it can be created. And just like in ISAM, every node is on a disk page, occupies a disk page with all the requisite information. And entire B+tree can be thought of a file consisting of pages where nodes are contained in each page. To understand the structure of the node, here there are certain examples are created here. You observe one node with 3 entries, 3 such key values, 20, 30 and 40. There are 4 pointers pointing to the children, and the pointer to the below of 20 or to the left of 20. There are 2 representations are here. One is below, and in the lower one it's a left side. So we can follow any one of them. Here the pointer which is below 20 should point to a node which is a child of that, and whose key value should be strictly less than 20. And the second pointer, which is actually in between 20 and 30, should point to a node where the key values, such key values or the key values should lie between 20 to 30, inclusive of 20, and should be strictly less than 30. And another pointer between 30 and 40, 30 less than or equal to k less than 40. So it points to a key node with key values strictly less than 40, and equal to or greater than 30. Similarly, the last pointer should point to a node with k value greater than or equal to 40. This is how we can visualize every node in the B+ tree. Just another representation of the same node is given where the key values and the pointers are given in the adjacent form side by side, where key values serves as the separators for the pointers. And this is in case of non-leaf nodes, just pointers and key values are there. When it comes to the leaf node, a small add-on is there, small difference is there, that the records, actual records may be there or pointer to the records may be there in the leaf nodes. They are not key values, but either they are records with a particular key value or pointer to the records. So the leftmost pointer should point to the previous node, previous page pointer, actually previous page pointer, because in the previous slide we have seen that the leaf nodes are in the form of a doubly linked list. So if you take one leaf node, the leftmost pointer should point to the leaf adjacent to it. So it should be a pointer pointing to the previous page. And then a record or link to a record, that is R1, and then key value which supports this R1, and then record key value, record key value, like that it can be stored. And the right hand side, the rightmost part again should be a pointer pointing to the next page. So the these two pointers will act as a will create doubly linked list of leaf pages. So this is in case of leaf nodes, this is how the nodes are created. So non-leaf nodes are one type and leaf nodes are created in a different way. This is how we can observe the creation of the nodes. The structure of the B+ tree facilitates equality query. Given a key value, we can check whether data records with that key value exists or not. And range queries, given a pair of key values, whether records exist with key values between those two values or not. And it also facilitates insertion of new records, and the B+ tree gets adjusted automatically with respect to the new data entry if required. Similarly, deletion is also facilitated, can be facilitated very easily. It automatically shrinks if required. The tree automatically shrinks. So given a B+ tree, we can observe how search can be done. Given a key value, we start with the root node, and based on the value of the key value, we can trace along the subtrees until we reach the leaf node, and in the leaf nodes we can search whether the data entry exists or not. For example, if you want to search whether 60 key value 60 with key value 60 data is present or not, if you want to search, we start with the root node with 80 as the root node starting value, and 60 is less than 80, so trace to the left subtree of 80. The key value is 20 is the starting key value of the left subtree, and 2060. So this first value, pointer value, is less than 20. The next pointer value is between 20 and 60, but still it is strictly less than 60. So the third pointer actually should point to the node whose values are greater than or equal to 60. So the third pointer points to the node which starts luckily with 60, and once 60 is identified, again you can go for the second pointer, which actually starts between 60 to 65 inclusive of 60. So the second pointer actually points to 60, data record with 60. So that is where you can observe the record with the value 60. Now let us try to observe actually how the insertion takes place in a key value. In this case, let us see an example with the root node consisting of 4 key values 13, 17, 24 and 30, and children are there with 4 children are there with that root node, and they are all leaf nodes. Now suppose if I want to insert 8 into this, starting from the root node, 8 is less than 13, so go to the left child of that, and then 2, 3, 5, 7 are the key values over there, and it is already full. the capacity is full, so we cannot insert 8 over there. So then what to be done? I have to split that node of the leftmost node, and middle one has to be popped up. The middle one can be 3 or 5 of course. In this case, let us pop up 5. So pop up 5 under the above range, so that the node is split into 2 parts. 2, 3 is one part. Whenever you pop up, you repeat that. 5 is repeated over another node. 5, 7, 8 is another node is created. So that node has split into 2 nodes basically. 2, 3 in one node. 5, 7, 8. 5, 7 is another node. Another node is created. Since a new node is created and 5, 7 are the values, 8 can be inserted there because only 2 values are present in the node. So 5, 7, 8 can be inserted over there. 8 can be inserted over there. Once we push up 5, a new node is created, but any node should have a minimum occupance of 50%. So one entry is not sufficient. A minimum of 2 values should be there because the size is 4 over there. So one more value has to be inserted over there. So to do this, what actually is done is, since the root node is already full, anyway we are creating one more level. So to facilitate more space, what we do here is we split the root node. We downgrade the root node values to the lower level. So 17 is left over there, 13 is given to the lower level. So 5 and 13 will occupy the child node, newly created child node, and one more node is created with the values of 24 and 30 at the same level of 5, 13. One more node is created, and so because of this, what happened is the level of the height of the tree has gone up by 1. Previously it is only level height 1. Now the height has increased to 2. And root node, space has been created. In the root node only one entry is there because the root node can have only one value, but all other nodes should have a minimum of 2 because of the size capacity restriction. And because of this, 513 is the second level node, and 2430 come to the second level, and after that 23 is the leftmost node in the leaf part, and 578 and the remaining nodes will be as it is. So because of the insertion of 8, what happened here is we have created, because since the size is full, capacity is full, we have created a new node with new values. So this is how we can insert. This is one way of insertion. This is not the only way of insertion. This is one way of insertion of B+TREES. The process of insertion that we have seen in the previous slide is summed up in the form of a step-by-step process. If traverse and find the correct leaf node L, if L has enough space, then just add the value there, and stop. Otherwise, if it is full, split L into 2 nodes, L and L dash, and redistribute the entries of into L and L dash evenly, and copy up the middle key value, insert index entry pointing to L dash, new value into the parent of L. And if a non-leaf node is also full, recursively do this, recursively redistribute the values until the root node, and the capacity, 50% capacity rule is not violated, until it is not violated. So we keep on doing this until we reach the respective root node. And that's how the insertion can be observed. And one more way of doing insertion is depicted here in another example of insertion of the same value 8. Previously we have created one more level and the height of the tree has been increased. Here we see one more way of redistribution with the sibling, which is co-child with respect to the same parent. We can redistribute the values into the co-children, but it can also be done. In this case, insertion of the same value 8. If you observe the root node, previously height of the tree is 1 only. The root node consists of 13, 17, 20, 24 and 30. So instead of creating one more level, what we did here is, since the last node is already full, 2, 3, 5, 7 is already full, the value 8 is inserted in the root node instead of 13. 13 is replaced with 8. because in the root node it is only a value pointing to the lower level. It's not any record, it's not a record. So we can change the values of the entries of the non-leaf nodes. So the value of the non-leaf node is changed from 13 to 8, and all the values of 2, 3, 5, 7 points to the left of that are less than that, so there is no harm in that. Still they point to the left of 8, and the value of 8 now inserted into the second node. They are readjusted and it is inserted into the second node. So now the second node consists of 8, 14 and 16. This is redistribution of the values with the sibling. This is called redistribution with the sibling, because the adjacent nodes have that capability to adjust. Because it is possible here, it can also be done. This is one way of doing things. The previous one has an advantage of creation of more space. Insertion of the more nodes can be possible. In this case, the space is more occupied, but height is still 1. That's the advantage here. Now when it comes to the deletion part, again start at the root node and trace to the node where the entry is present to be deleted, and delete that entry. If the deletion of this is not violating the 50% occupancy rule, fine, you can stop there. If it is violating the 50% rule, if the node occupancy is less than 50% because of the deletion, then now we have to redistribute. Now we need to adjust the nodes. Now in this case, instead of creating new nodes, we have to merge the nodes, because the data is shrinking. We have to merge the nodes. So if the data is less than 50% in a particular node because of the deletion, then we have to merge the node with the corresponding at the same level or with the root node, and this process has to be recursively carried out until the root, so that at every level 50% rule is not violated. And this is how the deletion can be accomplished, and we'll see an example how this can be done. Now we'll see an example of deletion. Let us consider a tree with height 2 with the starting root node having 17 value, and 5, 13, 24, 30 are the first level, and then the remaining data nodes are there, 2, 3, 5, 7, 8, 14, 16, so on. Now if I want to delete 20, starting at the root node, 20 is greater than 17, so go to the right of that and go to the 24, 30 node. 20 is less than 24, go to the left child of that. 19 is the starting value, trace along that. So 20 is the second value, so you can remove the value of 20 from that data node. If you remove the entry of 20, so 22 can be moved forward into that location. Now the node consists of 19 and 22 in the data node, and still the occupancy is 50%, so there is no problem with that. We can stop there. That's the first case of removal of 20. Now when it comes to in the second instance, after removal of 20, still if I want to remove 22, again trace, like in the previous case, you trace and reach that node of 19. Now in this case 19, 22 are remaining in that fourth data node. If I remove 22, this capacity of the data node has come down to below 50%, so which is not acceptable. Then we have to readjust. There are various ways we can do that. Here one way is, since only one value is there, 19 in the fourth data node, immediately we can shift that data node to the left which is left data node which is connected to that. Shift the value of 19 to the third one, 14, 16, then 19 you can add up there, still because there is a vacancy is there for that. Now at this juncture, if I want to delete 24, then we can reach the data node 24 starting from the root node of 17. Once we reach 24, if I remove 24, since the data value is already copied up in 24 in the index value, that has to be removed. So now once we remove 24, the node consisting of 24 and 30 falls below the capacity of 50%. So again we need to merge the nodes at that point of time, because 30 is the only value that is present and 24 has been deleted in the data node. Now because of this, we can merge the nodes at level 1, 5, 13, 13 and 30, and again the root node consists of only one value. We can merge all these nodes into a single node, 5, 13, 17, 30 forms a new node, so that both the nodes at level 1 merged together with the root node. All the three nodes had become now only single node, 5, 13, 17, 30, and we can readjust the values of node values. 24 is also deleted. So this is how we can merge the nodes. Because of the removal of 24, the level has been decreased. So the height of the tree has decreased now to 2 to 1. This is one way of merging the nodes. One more example is presented here where the merging is not possible sometimes, because after deletion of 24, if you observe, the node with at the same level of 30 is already full, so I cannot merge with that. So in this case, one possibility, this is again one possibility, it's not the only one. One way of readjustment is done here. 17 is moved up, 22 is copied down into the lower node, and so that the occupancy is more than 50%. And now the leftmost non-leaf node 5, 13, 17, 20 has capacity is halved. 5 and 13 will remain there. 17 goes up, 22 comes down into the right node, so that the occupancy is adjusted now. This is one way of redistributing the values of the nodes, so that occupancy of 50% is taken care, and the number of children, restriction on the number of children is also taken care. This is one way of adjusting in case of deletions. So far we have seen the insertions, deletions on the B+ tree. But when it comes to the initiation, when there is no B+ tree at all, and we have the data to be inserted, or a B+ tree has to be created at the beginning, when there is nothing, no B+ tree is existing, then how do we start? Again, there are so many ways in that. One way is start with a root node, then keep on linking the data pages. As one more new data page is inserted, then create a new node, split that root node into two nodes, and the one level is increased. We can do this recursively until all the data is inserted. It seems to be fine, but the problem here is that every time the tracing has to start from the root. As the tree grows, it's a time-consuming process. Unnecessarily, you have to start from the root again and again until all the data is inserted. But still, that is one of the options. And one more option, easier option, is the bulk loading option. It is called bulk loading, where the data is first sorted according to key values, and then returned to the pages. Starting from the first page, whatever key value is existing, that key value, based on that key value, a node can be started with that key value. In this case, let us assume that a node can have two values, and each data page consists of two records. Let us assume that. So based on the key value, we can keep on inserting the values into the node. Once the node is filled, according to the capacity of the node, once the node is filled, in this case 2 is the capacity, once 2 entries are filled, then we have to increase the level. So in this case, the starting values are 3 and 4 is the starting value, and the next highest value 6 and 9. So we started a node with the second page, starting value of the second page, because first page already consists of the values which are less than that. We can link them to the value. So the starting value is 6. So 6 is copied up onto the first node. Once 6 is inserted, the left hand side of 6 is linked to the first page consisting of 3 and 4. So 3 and 4 are linked, and then the capacity of the page is full, 3 and 4. After the second page is read, 6 and 9, which is actually the linked to the right side of 6. And then the third page, starting value is 10, that is copied up, 10 is inserted there, and right side of 10 is given to the third node, third data page. Once it is done, at that level, the capacity of the node is full, 2 is full. Now, still if you want to insert one more data page consisting of 12 and 13, so that node is not enough. Then we have to split it up, and one more level is increased, one more node is added. Again, the values are to be readjusted now here. So 6 is left over there, and 10 is copied up. So 6 becomes the left node of the 10, and one more, the starting value 12 with the new page, the starting value of new page 12 is added to the new node created. So 12 becomes the right node of 10, and like this we keep on load the values until all the data pages are entered. We keep on adding the nodes. Once a node is filled, then we'll increase the size of the level of the tree. We'll keep on doing this until it is filled. Again, this has certain observations here. Which node has to be split is an issue. All the time what happens is the rightmost node above the leaf node will be split. Once it is filled, it will be split. That's how we need to process. This may have certain problems. Again, if you look at this example, all the data pages are consecutively ordered, and the non-leaf nodes, once they are newly created, their occupancy is only 50%. So still issues are there with that. We need to readjust after once a tree is created, we can readjust the values. So this is how the bulk loading actually works out.